Welcome to the afternoon session. Our next speaker is Tiago Pereira, who's going to talk to us about dynamics of heterogeneous networks.
I would like to thank the organizers for the invitation. It's a big pleasure for me to be here. I started studying dynamical systems about 2001. I was studying with Soto. So he gave me a paper to study. It was this name-mark cycle verification. So he gave me this real Takens paper. And about half the paper, they talk about if you perturb a flow, you can have chaos, right? So they put axiom A system there and so on. So I start studying this. I run into this book by Marcelo, Stochastic Dynamics of Deterministic System. So I told Soto. Soto told me, no, I don't want to touch this book. You have to study all by yourself. So, but then I was dating my now wife. And I was telling, oh, this book is amazing. Like, when I grow up, I want to be like this guy. He's just amazing. So, okay, so time goes on. I go for PhD in Germany. So I was at the Weierstraße Institute. And this friend of mine told me, we're going for kebab after the day, so why don't you come? So I told my wife, why don't you come? Like, we go for Hackashenmarkt, we go for kebab. So there we went. So I arrived there early. And then this friend of mine, he had another Viana, Ricardo Viana, which was a physicist from Paraná. So then, okay, we start chatting, my wife arrives, and I say, oh, Dani, this is Viana. She said, oh, I cannot believe that Viana is here. Oh, it's such a pleasure for me to meet you. Like, Tiago talks about you the whole time. And I said, Dani, why don't you go and get a kebab, please? I said, no, he really said, you know, you're like the biggest inspiration. He said, oh, well, you know, it's good to be inspiration for the younger generations. And I said, Dani, go and get your kebab, please. He said, no. And you know, he gets a book and says, like, he wants to write mathematics as clear as you write. And then, oops. He said, you know, Dani, I'm sure you know I'm Ricardo Viana, right? The physicist. Many people mistaken me by Marcelo Viana, the mathematician, right? And then I said, I told you to get a kebab. And then he was feeling the situation. He said, but don't you worry about it. Like, this is very common. So once I received, he's saying, I received an email from nonlinearity. It says a journal that will never read, I do not understand what is written there, saying, Professor Viana, it's a pleasure to invite you to be the editor of nonlinearity. And he replied, I'm sure you mean Marcelo Viana, the mathematician from IMPA. And he said, and then was only get worse. Then nonlinearity said, oh, we do apologize. There we go, 2 years of volumes for free of a paper that he cannot understand. So, okay. This is all to say that it's a big pleasure to be here in Marcelo's conference. So it was, since my early days, I was reading his book. This will be a joint work. We'll talk about dynamics of heterogeneous networks. And this is a joint work with Deniz Erolu, which is in Turkey now, Sebastian Van Strien from Imperial. So I started this work when I was myself at Imperial, and Matteo Tanzi. I think he did his PhD, or his actually master's with Marmi, who is here somewhere. So the talk today, my talk will be about a network of dynamical system. And a network of dynamical system will be given by this triple, which will be a graph, a dynamical system locally, and a complete scheme. What I mean is the following. So I will have this graph, and on the top of each node, I'm going to have a dynamical system. So in this talk, unless in the very end, what I will mention, my dynamical system will be x goes to 2x. I can complicate, but it's not really necessary. Everything I want to talk will be in this family. So then take a node of this graph. It's isolated. You're going to have x going to 2x mod 1. Then you take another node. This will be also y going to 2y mod 1. And now you couple them. By coupling, I mean, you know, one node will fill each other. So in this particular case here is a sign of the difference of these two states. Yeah? And this is a classical problem. If you change alpha, things can change. For alpha 0, Lebesgue measure is invariant. For alpha non-zero, you start having some bifurcations and so In general, you have any function h here. Yeah? So I call this h now the coupling function. So I have local dynamics, I have coupling function. But then what happens is that this node here, he will have many neighbors, and this will be given by this graph G. Yeah? So all the graphs G I want to talk about today will be graphs, I will not define the graphs, but they resemble this picture you see here. They will have groups of nodes. Sometimes I use the word clusters, so which you see here. And the rough idea of this cluster is that nodes that belong to a cluster, they tend to have more friends inside the cluster than the outside of the cluster. You can turn this into a mathematical definition, but I will not do it. And then, so I have this network with these groups. And on the top of this group, I will have another group of highly connected nodes. They will appear in red in this talk. And these highly connected nodes, I will call them hubs, or people call them hubs. Yeah? A group of these highly connected nodes, I will call them rich club. Yeah? This is the common name, this name that appears in neuroscience. So for this model now, for this general graph, I can write the model, which I wrote for 2 nodes. So I'm going to have, I now denotes the nodes that I'm sitting in. So t plus 1 is the next state. So I have the local dynamics, which here for me is x going to 2x. Then if alpha is non-zero, I fill all my neighbors. So this aij is 0 if I and j is not connected, 1 otherwise. And then I have this coupling function here. So the goal of this talk is to understand this dynamics. I will focus, as I said, so on this kind of networks. I will call these networks heterogeneous. Why? Because some nodes, they have only a few connections, and some other nodes, they are massively connected. So the number of friends that you have in this graph varies quite a lot. Yeah? So this is heterogeneous for me. These hubs, what people have been studying now for kind of 30 years now, these hubs, the existence of these red nodes, they have a huge impact in the dynamics of these networks. So experimental results in the brain shows that once this red node starts to have some kind of dynamical correlation, this sometimes can be very good for the network itself. So if the network's growing, you need this dynamical correlation for the network to grow properly. This is what's proven in this paper. On the other hand, if the network has already grown, and you start getting dynamical correlation in this red blob that you see, then actually this is associated to some kind of pathology, some kind of epilepsy. Yeah, so kind of it's very important to understand whether this correlation will emerge, will not emerge, so you can control, you can destroy or improve. So this is kind of the problem I want to tackle. So that said, so if the setting of the problem is clear, in this talk I'll have 3 goals. And they will be of increasing complexity. The first goal will be like some natural goal. You give me this triple, graph, local dynamics, and coupling, and you want to predict what's going to happen as you change alpha. As you change alpha, the system bifurcates. You want to see how dynamical clusters appear and so on. So this is more direct. So you want to tell what's the new dynamics of the system. A slightly way more complicated problem is the inverse problem. You give me the data of the system now. You go measure what the network's doing. So you give me the data, and then I'll tell you which triple generated this data, which graph, local dynamics, and coupling. So this is a problem. If you think for 5 minutes about it, you're going to see that it's not unique. It's a very complicated problem. So. And the dream, sometimes you can do, sometimes you cannot do, is to close the loop. So you give me the data. I tell you which dynamical system generated, and then you do bifurcation theory and tells what's going to happen to the system. So this usually goes pretty bad, but in certain situations, you can prove some results. OK, so let me start with the first goal, if this is clear. If you think about, or most of the times you do numerical simulations on this problem, if you run numerics, you're going to see some challenges. First of all, the attractor of the system seems to be a counter set, some kind of fat solenoid. 2 is very hard, at least hard for me. I did not manage to do this, to write some kind of perturbation theory for this problem. Because you have this, some nodes that are poorly coupled, some nodes are highly coupled. So there's not really a perturbation scheme, yeah? So these hubs always couple strongly. The other pain that you have when you have these hubs is that perturbations, they will spread in this network super fast. So the diameter of the network is very small. So if you have a regular graph, the diameter is the maximal geodesic path between any two nodes, right? So if you have a regular graph, the diameter will be like proportional to the system size. But here, the diameter is log of the system size. And we heard here that log is not a function, so log of a log then is nothing. So the perturbation is felt super quickly. And if you do some thinking, you're going to see that in all interesting situations you want to study, the unstable manifolds are very high dimensional. So this problem seems very complicated to solve. But if you do a 5 minutes thinking on the back of the envelope, you start thinking that actually I will succeed solving some of these problems. So let me tell you some of the heuristics of this problem. So the idea is the following. So I have here a poorly connected node. So this node has only a few connections. Couplings is small. So this collection of these nodes, they should be almost independent. So they are not independent, but you know what? Let's fake it. Let's say that's independent. So if it's independent, then you can go to the main guy here, to the hub. And the hub will have lots of these inputs, right? So you can think of you going to some kind of law large numbers now. So that's the idea. So if this was true, then you could write all these high dimension contributions that this highly connected node is feeling in terms of a mean plus fluctuations. So that's the idea. And the problem really is that these nodes, they're not independent. As I said, the correlation will spread through the network quite quickly. And actually, although the system is super hyperbolic when alpha is 0, when you keep on pushing alpha, you lose hyperbolicity. So you have some problems, but this mean plus fluctuation should work very well. So the idea here is that if you can do this scheme here and get it to work, you want to find equations for the mean. And you want to control the fluctuations, so you want fluctuations to be small. We succeeded proving some of things for this system. And this is an informal statement that we published in the Journal of European Mathematical Society. I will not bother you with all the assumptions or hypotheses, because there will be quite a few hypotheses of the network. So for this statement here is my f is x goes to 2x, as I promised. So here's saying if the coupling function H is smooth enough, the number of hubs is very small. This is a natural assumption. If the number of hubs is large, then you're back to a homogeneous case. So the number of highly connected nodes is very small. The number of friends, this means the degree of the hubs, they should have a given scaling, which is in this case is very natural, square root of the system size. If these assumptions are met, then you can prove the following statement. There is a set of initial conditions and a time, so it's a finite time statement, but this time is exponentially large, such that for the hubs, or for a set of nodes, you get this effective description here. So all this high dimensional problem was written now in terms of mean interaction plus fluctuations. So this is what I promised, and this is what we are delivering now. So the idea is the following. So over finite time, I do not know what the system is going to do over infinite time horizon, but over finite time, this time is very large. You can do the following. You can write the system. Actually, this is a dimension reduction statement. So you can write this high dimensional system up to a small fluctuation, which you can control. So this fluctuation will be very small. What you get, so you get, by neglecting the fluctuation, some kind of effective description of your system. Yes, and this is kind of dimension reduction. So I started with one-dimensional dynamics. So on the top of this hub now, I have a one-dimensional system, which I can study and so on. So now I have to study this family. But this is a much easier problem to study. Yeah? And as I said, this time is exponentially large. So actually, if you do simulations, you never see this breaking. Yeah? But we construct some counterexamples where this breaking always occurs with probability 1 and so on. Yeah. So as I said, so dimension now is very low. This allows for prediction. And there's another big thing. I'm not giving you the formula. But we have a formula for G. So we know the expression of G. So in particular, if we could invert this expression. And we know a formula for kappa, which will depend on the hub. I told you this is up to fluctuations, so something you're ignoring. These fluctuations, they are not random variables. They're actually dynamically generated. And these fluctuations, they will be correlated in space, in this index I, and it will be correlated in time. And this will play a big role in the future. Yeah? But this kind of ideas goes back to goes back to Zwanzig. So this idea of formulation of statistical physics. So there are ideas like sometimes you have fast dynamical variables, slow dynamical variables. So his idea is that you should neglect fluctuations. But here, these fluctuations, they will play a big role. Let me tell you how you can aim of proving such a result. So what's the idea? So I have here now my phase space, which for me is the torus. So I have here the torus. And what I want to do, let's recall, well, I want to neglect this fluctuation. So I look for the portion of this phase space where this fluctuations is kind of very large, is larger than what I want. So this will give me a set. Okay, inside the set, I lose control of the system. The system is not hyperbolic, can be total mass. But the idea now is to do the following. I will truncate my system inside this bad set. I will induce now two systems. I will have the true system and the truncated system, or the system that I do the surgery. And I'll do the surgery in such a way that this truncated system is now hyperbolic everywhere. I can study everything I want. And then I want to transfer what I learned from this truncation to the real system. Yeah? Okay, so the idea will be the following. So now I can turn my problem into a hitting time statistics. So here I have my torus. I will have unstable manifolds in the horizontal plane, stable manifolds in the verticals. So here's the bad sets drawn in red. Here are the bad sets. And I have here my initial point. So outside of the bad set, I didn't do anything to the system. So the truncated system and the real system is precisely the same. So let's say I evolve by the truncated system. So I get a new point, I evolve again, then evolve again, bang, hits the bad set. So now I have to make a choice. I continue with the truncated system. Okay, so the problems, what I'm telling you is the following. So if you cook this problem clearly, or let's say if you cook this problem this way, you can you can compute the time where you control the fluctuations as a hitting time statistics, right? So how often do I hit this bad set and so on. So that's the key idea. And if you did this properly, now your truncated system is hyperbolic, has cone fields and so on. You can use ergodic theory for it. You have to do some work. And this paper, most of the works is this graph transform estimates, because basically what you need is that this truncated system will give more importance to this bad set, right? Some kind of Katz formula will appear in this game. So basically what you need to prove is you need to prove that this truncated system will have a SRB measure, and this SRB measure will give more importance to this bad set. So if you do this, then you solve the problem, basically. Yeah? Okay, let me give you one example of how you can use this. So that will be my x goes to 2x. I'm choosing now this coupling function here. And what I'm going to do, I'm going to get this network you just saw with 4 communities. Which community will have 100 nodes? Initial conditions are uniformly distributed. And then I do simulations. So in red now, you're going to see the simulations. And in solid lines, you're going to see the prediction from this theory. As I said, so you can use this approximation to do the prediction. So what you see this. So in the cluster, so the blue nodes, they will be chaotic. So the red nodes, the result of the simulation. So here you see the return map for this dynamic. So here's xt plus 1. So basically you see this function, the doubling map. I'm not sure you can see there is a solid line there. So the prediction is actually fairly good. And for the hubs, what you see, the hubs, if you do numerics, the hubs, they look very periodic. So this is the function now for the hubs in this case. So in this situation here, if you do the simulation, what you're going to see a huge transition towards periodic dynamics in these hubs. They explained by this theory. Yeah? So you're going to see these hubs almost lock in this period 2 orbit. They will all be locked. Yeah? So here's the result of the simulation in red. And as I said, so in black is the map that we deduced. So this can work very well, at least for this class of examples. So what I want to do now, I want to do applications. So I want to do what we call the inverse problem. If I continue with x going to 2x, and if my network's very large and so on and so forth, I can prove everything. But I will spice it up. I will consider this inverse problem in a setting that I cannot prove, but it works nonetheless. And then you have to solve it, not me. Okay, so I want to do now the recovery from this data. So I have this network now. And my assumption is that I'm going to measure the state of every node of the network. So here I'm giving you one possible state. So this dynamics here is 2-dimensional, not 1-dimensional. I'll mention which dynamics I'm choosing in a second. But this means now I'm measuring everything, also all dimensions. Yeah? And I'm going to get this plot here for all nodes of my network. So in the x-axis is running time, and the y-axis is running a given state. So this is called time series. And I get time series for all nodes. So the problem is the following now. If you give me the time series of all nodes, I want to classify the time series into groups. I'm going to say, well, this bunch of data belong to the same cluster, this bunch of data belong to the same cluster, and so on. And then I want to tell who from this data is the rich clubs. So which ones are the highly connected nodes and so forth. It's quite interesting. So we try with pure machine learning techniques. So for example, if you try to train a neural network to classify this, we failed. And then we went next door to the machine learning people, knocked his door, gave the data, they also failed. So it's kind of it's a non-trivial problem is what I want to say. But let's have a look at this dynamical system we obtain. And so the insight is here. If you have a look at this dynamical system, so this will be the model equation. So this is only valid for chunks of time. If you take too much data, so this is also a philosophical problem. If you take too much data, you see high dimension. But if you limit the amount of data you see this small dimension excursions. Yeah? So this small dimension excursion should be modeled by this equation. This is my main claim during the first part of this talk. And this is low dimension excursion will have some kind of chaotic evolution. So we're going to have chaos. And then you have this fluctuation here. Yeah? Okay, so this means if you take the time series, then this time series is a sum of two things, deterministic chaos plus fluctuations. Telling deterministic chaos from fluctuations in general is a big problem, so you cannot really do it. So that's also why machine learning techniques fail. But my main content here in this second part of this lecture now is that this fluctuation, they're actually dynamical fluctuations. They're not noise. They will bear properties of the structure of the system. Actually, you can prove the following thing, that this fluctuation can be decomposed into two parts. One, which would be independent due to the Kerr correlation, and one which would be common. And this common noise, now this common fluctuation will measure the network structure. Okay. So to tell you how this relates to the network structure, I have to introduce an index, which people call topological index. Yes? Yeah. For small chunks of times, yeah. And it depends on actually, this is a bad notation, I see what you mean. Because this psi I is not psi I, it's psi of everything. Yeah, yeah. I say everything that I don't like, I write as psi I, but there's psi of lots of indices. Yeah, so thank you. So this is a bad notation, but yeah, this is what I mean. So you're going to get all these dependencies here. Yeah, into this chunk. Yeah. Thank you very much. And this will be felt here now. This will be felt in this common noise. So this common noise now will measure all this common index for me. So this is in, let's say, in this graph theory, in this network science, people introduced this. So gamma I is the set of neighbors of the ith node. And they have this thing is called matching index. So the matching index between I and L, there will be the set of common neighbors between I and L. So you can prove the following statements if you do not overdo in coupling strength. So if coupling is still small, then you can prove that if you do not exceed this coupling, and if you measure the covariance of this process, of this noise, or this fluctuation, then will be upper bounded and lower bounded by this matching index. So basically what I tell you is that if you treat this data and get this fluctuation term, is measuring a network property, which is how much common neighbors I and J have. And so the key idea is that this fluctuation, they will reveal the cluster structure of your system. And because cluster is basically defined by having high match index, so this is actually deciphering the cluster structure for you. So that's roughly speaking, the idea. So the idea, now we have a recipe. So if you give me the data, I'll try to split chaos from this data, and then try to get the fluctuations to read the network structure. So that's kind of the recipe. So let's implement this recipe now in a model. So this was the simulation was done by some friends of ours from Barcelona. They belong to this Blue Brain project. So they took the cortex of the cat, which was measured experimentally. So that's why you see these funny names and these funny colors. For example, the blue is the visual cortex. Then orange is the auditory cortex, and so on. In red here, you see the nodes enveloped by red is the rich club. So on the top of each node, this will be a simulation study. On the top of each node, they will put a bursting neuron. So it's a multidimensional model, basically, think like this. And they will couple these neurons with some kind of, they call chemical synapses. There are a couple options, but they do chemical synapses. So it's kind of sigmoidal function, kind of complicated. Then they do the simulations, they give us the data. I get the data, I do the procedure I told you. So when I get the data, the first thing to do is to look for this low dimension excursion. So the data can be very high dimension, but sometimes it can do low dimension excursions. So how do? We do Takis embedding. So by Takis embedding, you take a chunk of data, you do the embedding and measure the dimension of the system. If dimension is very small, I classify this chunk of data as being low dimensional. Yeah, so this is the first step. So if I classify this chunk of data as being low dimensional, then I can do some kind of splitting problem. I can do some Bayesian inference to learn the function that's giving the data and break this from the coupling. So let's say I do this. So then I can filter this deterministic chaos from the data, right? I can filter this out. I can just subtract. I'm left with the fluctuation. And then I do this analysis on the fluctuations. So if you do all this procedure, then you're going to find the following thing. So here's the real network map that people obtain experimentally. And here's the reconstructed. So it looks quite good. It's not perfect, of course, and you see the auditory is less dense and so on. Some nodes, they get misclassified. For example, this node here is to be blue. Now in this recovery is pink. So it's not perfect, but by naked eye looks good. So the natural question is, how good is this? And okay, so we asked these guys, we need more data, we need to do this very systematically, and so on and so forth. Okay. So they gave us more data, we did more calculations. So this plot here takes a couple, takes a couple weeks to do. So the idea is the following. So here's the coupling strength. In the x-axis that you see is alpha. And the y-axis is the probability that I put a node in the wrong cluster, the total probability. So what they do for each value now of coupling, they do 100 experiments. They give us this 100 data, we do this classification, and then we count how many nodes we're misclassifying, and then we do this plot here. So you see that here's the mean error, or the mean probability that you misclassify data is about 5%, and in this shaded area, you see the fluctuation. And this is kind of 5% all the way through up to a given point that this seems to be exploding now. But in general, 5% mistake, which is very good. So with 5% mistake, you can predict transitions in this rich club. Because basically, its collective motion is very stable. So now I will enter the third thing I wanted to do. Because so the idea is like, we proved the theorem that says your data can do low dimension excursions. You can dig this from the data. You can reconstruct the problem. Then the idea is now is to close the loop. So to close the loop, I will close the loop in a very particular way. I will take this cat cortex. And my goal now is to predict, so you give me the data, and the network is, let's say, healthy. So there is no strong correlation in this dynamical system. And I want to predict from the data. So the idea is like, you give me the data when the system is healthy. So healthy here for us means no strong correlation dynamically. Then I will reconstruct the system. And then I'll tell you the onset of strong dynamical correlation. So that's my goal now. This is an important problem because people, as I told you in the beginning of this talk, strong dynamical correlation in this set of red nodes means some pathology for the system. Okay, so let's do the following. So this tip into strong correlation in this literature people call critical transitions. It's kind of some kind of bifurcation, but bifurcation is not sexy these days, so they changed the word. So I will call critical transitions. I will also use this kind of word. So if you see here, the x-axis is again the coupling strength is alpha. The y-axis is something that I will not give you the formula. It's called order parameter. It's a measure of correlation. So it's a measure of correlation, global measure of correlation between all nodes of this rich club. So between all hubs. The important thing for us to know is that if this measure is close to 0, then there is no correlation in among these nodes. And if this measure is 1, think that if you measure Pearson correlation between these dynamics, it's kind of super correlated. Okay, so now the experiment starts. So this starts simulating the system. So here's the first simulation, second simulation, third. They offer me, I could take any data, so I took this data here. So here's just the time series that you see. So here's in x-axis is time, and the y-axis is a dynamical variable. So this looks pretty much chaotic or noisy if you want. So we get this data, and in this data set, we do this dynamical procedure changing. So we split the data into chunks, see whether there's a low dimension excursion. If there is, we take this, do Takens reconstruction, blah, 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 as you saw. Get these fluctuations, reconstruct the system, and so on and so forth. So once this is done, you get a model now for this data. And once you have a model for this data, you can go on the computer now and do simulations for your model and see what's going to happen. And once you do this, you're going to get from this reconstruction problem that the system will tip towards high correlation when the coupling is around 0.4. If this prediction is good, this will be a great prediction because we are very far from the bifurcation, right? So no. I'm taking so the underlying networks is still this cat cortex. I didn't change it. I mean, they're simulating the system, right? No, I mean they are connected. The network is connected, but not all nodes are connected to each other. I mean, maybe we fight for the definition of rich club. So they have some definition. So this is a rich club. But in the rich club, not all nodes need to be connected. The idea is that highly connected nodes, they have a tendency to connect among themselves. They are highly connected and also connected among themselves. Yeah. Yeah, the coupling. Yes, yes. Without changing the topology. Thank you very much for your question, yes. So the topology is fixed. Everything was fixed. The model is fixed. The only thing that's changing here is the coupling strength. And then by only changing the coupling strength, we say if you only change the coupling strength in your simulation, you should see a tipping around 0.4. Because this was simulations, you can continue the simulation. And here's our prediction. So around 0.4, you should see a transition to synchrony. So you see now the nodes are spiking together. This kind of happens. So now I don't know, because I didn't define critical transitions, we can argue whether I got it correct or wrong, whether here was the critical transition or here's the critical transition. But we're already super happy with this result.
When you say that they are synchronized, it means that there is a attracting periodic transition?
For this case, will be yes. But sometimes people, synchronization will just means like there is a, normally hyperbolic manifold for the system.
But in this case,
yes. So very boring. Or in this case, it's just attracting. In this case, it's total mass. The system is not hyperbolic. I only care about finite chunks of data. But if the system was x going to 2x, then you could prove this was corresponding to attracting periodic orbit. But you see, I can write the equations, but this map has a parabolic point. It's very disgusting. Okay, so this is the critical transition and so on and so forth. I have two things here to say to you. So if you use this theory of dynamical system and so on, sometimes you can prove everything you say, sometimes you cannot prove, but even if you use what you learn from the times you can prove, you can learn a lot of things and you can recover the system. Yeah? And if you do this blending of dynamical systems, so dynamical insights plus machine learning, you can do a lot of things. So in particular, predicting what's going to happen and tipping points for the system and so on. But I want to finish with this experiment now, because the other one was a computer experiment. You could say, well, computer experiment is kind of cheating, right? So how about the real things? Okay, the real thing. So we spoke to some friends in Maryland. They are laser people. So laser is basically PDEs, right? So if you look at the laser models, like you get this Lang-Kobayashi equation, so very complicated. I know nothing about PDEs, by the way. So anyway, so they designed this experiment, very nonlinear coupling, nonlinear this, nonlinear that. And they do this complicated scheme. Oh, this is, by the way, this is Roger's Roy group. We have some people from Maryland here. Maybe you heard of them. So anyway, and then they give us the data, nothing else. So it's basically some kind of PDE model with this 17 things, complicated and so on. But they told us, look, this is the network that generated the data. So they told us what was the network, so our goal now is to recover. What do? We do the same thing as I told you before. So I take the 17 nodes. I chop the system into chunks of times, and I look for small dimension excursions, low dimension excursions. So if I find low dimension excursions, I do Takens reconstruction. So if you do Takens reconstruction, you're going to see that unimodal maps is a very good description for the system, although the system is a PDE. Okay, so we learned this unimodal map, this family. Then we do this filtering. We learn the system, we learn the coupling. We filter the chaos from the data. We get these fluctuations, and then we analyze the fluctuations. This is what I said. So you have to do this. You have to be clever when you use this window. If your window is too big, then you get these high dimension excursions, and this is not useful. So you have to throw some data away. But if you succeed at the end of the day, you find the following thing. So here's the actual network that they simulated. And here is the network we reconstructed. And surprisingly, we just got 2 links wrong. But this is 2 links, it's 2 mismatch out of 300, right? Roughly speaking, because this is a 17 node. So, and then I will not bother with the details. We did the bifurcation theory for this. It fits very well and so on. So kind of, this was kind of, at least for this case, was a successful story. This does not work always. For example, if you try to simulate some kind of Lorentz dynamics, some attractor that has a fixed point kind of sitting in the middle of it, then it doesn't work. And I do not know why, but my intuition says that because you spend too much time near the fixed point, and this can spoil all fluctuations that you have. But sometimes works, and this is a success story of this approach. So bottom line is, if you do not care about syntactic time, sometimes if you want to have a finite description, finite time description, you can learn a lot from the system. And you can do quite a bit of bifurcation theory for it. And if you use dynamical system ideas together with some kind of machine learning ideas, you can do very powerful predictions. And the conclusion is happy birthday, Marcelo.
Are there any questions or comments?
So what happened, assume that you play the different game, no? So you have all the nodes, all independent, and each one you have the doubling map, okay? And then you have your, how do you call it, connection function, H, with a small epsilon. But instead of the bifurcation will be first you connect 2, then 3, then 4, 5, until that you go to the fully connected. Can you explain how is the transition diagram of bifurcation diagram? At the beginning, when they're all independent, there is expanding map. When it's epsilon is small, H is reasonable, and you are connecting only 2, it remain expanding.
Yeah.
When you increase more and more connections, maybe you start to see the appearance of attracting periodic point. Can you describe what is happening?
I think you mean something like this, right? So I have here a layer, so no connections. And then this feeds to the next layer.
2 connections, 3
Yeah,
connections.
yeah. Oh, this is, by the way, what people know, they know this is a great way to synchronize systems.
Okay.
This is called a sync-fire chain.
So if you go to the totally connected, then you'll see periodic
Yeah,
trajectory.
yeah. But I don't think this is proven, but they do this numerics all the time. And actually, they don't do with this expanding map. They do with rotations. And then they see, like, if you keep on digging the layers, eventually you get synchrony. But I mean, I never seen a proof, but this is a very clever idea. Yeah. They say this is, this is important because they say this is models some kind of brain activity and so on.
Are there any other questions? Well, if not, let's thank Tiago once again.